Okay, let's now start digging into how memory allocators work. Okay, let's start with the assumptions made in this lecture. Okay, so first of all, memory is word addressed. Okay, so each word, each word can hold a pointer. And a block size, the allocator of free block size, is going to be a size that's multiple of words. Okay, for example, if here we have our heap. So we'll have, for example, have an allocated block here that happens to be 4 words, and I have a free block here that happens to be 2 words, and so on. Okay, another free block here, and so on. And this is a free block, and this is an allocated block. Okay. So let me give you an example. Okay, so that's the order we're going to make these calls. First, when we call malloc, this is our heap. Okay, this is our heap. And then when malloc says I want a block of size 4, we're going to allocate 4 words. Okay. Now you could say allocate 5. I'm going to allocate another 5 words. And it's like allocate 6, another 6 words. Then now we're going to free P2 and note that we're passing as a parameter a pointer that was earlier returned by malloc. Okay, so when we do that, this block is now free. Now we have some holes in our heap, and then when I allocate 2, we have 2 options. Could go there. We just chose it to allocate it here, and so on. One important question here is that when we were implementing this allocator, what information does it need to keep track of? Well, it needs to keep track of where the heap is, where it starts, right, and where it ends. So what is the size of the heap? And it needs to keep track of what parts of the heap are allocated, like this allocated, and what part is free. Okay? And also needs a data structure in order to find blocks we need to allocate it, and you need to also be able to know what parts, of course, know what parts of the heap are free, so you allocate it there and so on. Okay? Let's see what kind of constraints allocators have. So first, from the application point of view, it can issue an arbitrary sequence of mallocs and free requests. Okay? So, and free requests must be made only to a previous malloc block. I've said this 2 or 3 times already because it's actually really important. And allocator, from the allocator point of view, the first thing that's important to know is that they really can't control the number or size of allocated blocks. This is something that the application does. The application does the requests, and the allocator just serves those requests. So it doesn't really know what the application is going to need in the future. Okay? And we wanted to be able to respond immediately to malloc requests. Okay? So in other words, it cannot reorder or buffer requests. So it's a synchronous call. When you call malloc, when it returns, it has to have done the job. It can't just reorder them. It has to respond immediately, right? They have to be, so otherwise it creates a big problem. Of course, we only want to allocate blocks from free memory. If you allocate blocks from allocated memory, it's going to be a big mess. You're going to be overriding data from the application. That is not going to be a good thing for sure. It's going to create bugs and hard to find and so on. So blocks cannot overlap. Okay? So, and also, it has to align blocks. And by alignment, it means that the pointer at the beginning of the block has to be a multiple of a certain number. Okay? For example, the GNU malloc library allocates blocks in an 8-byte granularity. Okay? So this is just satisfy a bunch of alignment requirements. Okay? And, of course, once an allocated block has been allocated, it cannot move. Okay? So in other words, compaction is not allowed. Why? Well, imagine the following. You call malloc, you get a pointer, and now you assume that the data is in that pointer, and then the allocator just moves it around. If you don't update the pointer, then you're going to be pointing to stale data, and that's going to be, again, a big mess. Okay? So allocators have to follow a very strict discipline. And now, from a performance point of view, there's 2 components. The first one is throughput, okay? And that means the following. Given a sequence of malloc and free requests, the goal is to maximize throughput. Okay, so the goal is to maximize that. And the other component, by the way, of performance is peak memory utilization. We want to use memory, we want to have as few holes as possible. We want to use as much memory as possible. Okay? So, and these goals are often is often conflicting, because if you want to maximize throughput, you want to do things very, very fast. Therefore, you can't afford to do very sophisticated, do a lot of work in managing memory to increase peak utilization. So, and the throughput here is the number of completed requests per unit time. For example, you're going to do 5,000 mallocs and 5,000 free calls in 10 seconds. That's throughput. And what we're doing here is it will be a total of 1,000 operations per second, because we had 10,000 operations done in 10 seconds, 1,000 operations per second. The other performance goal of allocators is peak memory utilization. Okay, let me tell you what it is now. So again, we have our sequence of requests from R0 to Rn-1, and the aggregate payload PK is the total useful memory provided by the malloc blocks. Okay, so that's the payload P of a malloc block, is the number of bytes requested by the application. Okay. So say the aggregate payload PK is the total number of bytes that malloc provided, bytes requested by the application at request RK. Okay? And now we define the heap size, the current heap size, as HK, and it's monotonically non-decreasing, means it only grows as we need more heap space. Okay? And this is done with a system called sbreak, as I mentioned before. And now that we know, we define the current heap size and the aggregate payload, okay, which is the aggregate number of useful bytes in a sequence of malloc and free requests. What we want to do is define peak memory utilization as the maximum of the payload up to request K, right? That's the peak memory utilization at the moment when you call a certain request here, RK, okay? And so the peak memory utilization is the fraction of the heap that was useful in the past. Okay, remember that the heap never decreases, so that's why we're using max. Okay, so the peak memory utilization is the maximum aggregate payload divided by the size of the heap. Okay, and the goal is to actually maximize this number. We want to make the heap as useful as possible, whatever we're allocating the heap as useful as possible. Okay, why is this hard? This is hard because of something called fragmentation. It's all the holes that appear in our heap. Okay, and by the way, managing that has an effect on throughput because it has overheads. It takes work by the memory allocator to provide that. So let's see what fragmentation is now. There's two types of fragmentation: internal fragmentation and external fragmentation. And internal fragmentation is the fragmentation within a block. And the reason we have that is that this is, for example, here's our block, okay? And the actual payload is just a part of this block. The payload, that's what's useful to the application. And it's smaller than the block size. Okay? So all of these parts here that are not useful, they are the source of internal fragmentation. Okay? So, and this is caused by overhead of maintaining, space overhead of maintaining the heap data structures, like things like markers, whether the block is free or not, pointers among the blocks, and so on. Also, the padding for alignment purposes. We just said earlier that one of the requirements of dynamic memory allocators is that they need to provide aligned blocks. Okay, and also this internal fragmentation is caused by explicit policy decisions. Okay, so you could return a big block to satisfy a small request. Why would you do that? Because of performance reasons. Okay, so and one interesting thing about internal fragmentation is that it depends only on the pattern of previous requests, so it's easy to measure. Okay, so now what's external fragmentation? Well, it's external because it's external to the block. So that means that it occurs when there's enough aggregate heap memory, but no single free block that's large enough. So let me give you an example here. So suppose that we had this sequence of mallocs here, then we had a free. So we have 5 free here and 2 free. If I allocate 6, I'm not going to do that. So what happens? So actually I have 5 free here and I have 2 free here, so I have a total of 7 free. But none of them are large enough to honor this request of 6. So what will happen now? Well, nothing. We can. So, and by the way, this is actually dependent on the pattern of future requests. So it's actually difficult to measure whether external fragmentation is a problem or not. See you soon.